Welcome. This is last lecture for constitutive relation. Actually, in this lecture, before doing the summary, I thought we'll discuss about the Lamina constitutive relation. So, basically this word the Lamina, what does this means? Let us first give a definition what is essentially a lamina is. For instance, we are in today's age of composite materials. So, in a composite material, what you see is essentially a series of layers of material. For instance, it is called ply or woven fabric, or essentially a plane. So, those planes have negligible thickness or very small thickness and compared to other two dimension, and those planes are actually known as the lamina. A lamina is essentially a part of a laminate, where a laminate is essentially a series of lamina is arranged in a suitable order as per the material behavior desired. Essentially the lamina is a part of a or a is a plane which is a of very small thickness, that's which constitutes the laminate basically. So, the more detail of this lamination or laminate theory, or how the constitutive equation for laminate will be derived, it will be discussed in composite technology course or any other course possibly. Here what I thought I will describe that if there is a fiber orientation in this direction of a lamina, is essentially a lamina is a 2D body of very small thickness. So, this lamina is essentially a 2D body, and it is made of suppose woven fabric or any made of unidirectional fiber. So, these fiber directions are along this. Now, this direction what I say is the 1, 2 direction, and it is the material axis. So, 1, 2 direction is essentially the material axis. So, we write material axis. So, now our loading axis or the structural axis is essentially xy direction. So, when we solve this problem with a given load or stress, then we need to use the constitutive equation in terms of structural axis or the xy system. Now, in this xy system we already know that how to transfer these material properties from one axis to another axis. So, here I thought I will give a special case of a 2D orthotropic material or 2-dimensional orthotropic lamina, where the fiber axis and the structural axis is essentially different. So, now in that case, in a 2D orthotropic material, we know what is the constitutive equation, and the constitutive equation looks like this. So, here you see that there are 4 independent constants. I have already discussed these things in previous classes. So, these are the stress components and strain components. It is it can be also written is in this form, that epsilon 1 in a void notation, epsilon 2 and epsilon 6, this format. So, remember this is essentially the shear strain, gamma 1 2, and similarly stresses can be also be written as sigma 1, sigma 2 and sigma 6. Now, the relation between from the previous to last class, we know how these engineering constant and these mathematical constants q's here I have denoted in terms of q, because this q is coming from the essentially the plane stress constitutive equation. This is a body under plane stress, which we will learn in the next classes what is plane stress and plane strain condition. So that is not required right now. But here I have depicted the constitutive matrix in terms of Q. So instead of C, essentially C we derived for the 3D constitutive matrix, and 3D from there if we impose the plane stress condition, then you get the Q and Qij's. So that we will learn later. Now, this Q matrix, if I write it in terms of engineering constant, so there are in this fiber direction there are Young's modulus in E1 will be Young's modulus and E2 will be Young's modulus in this direction, and then the Poisson's ratios will be nu 1 2 and nu 2 1, and then the shear modulus between in plane shear modulus, which is G 1 2. So now among them these nu 1 2 and nu 2 1 both of them are not independent, as we know, because we know the reciprocal relations which can also be proved from the Bette's reciprocal theorem. So these nu 1 2 and nu 2 1, how it is related, we know that. So now finally the number of independent constants will be E1, E2, and one of them, say nu 1 2 and G1 2. So these fours are my independent constant, which is consistent with the 2D orthotropic material. Now with this we can write the Qij's, how it will look. So these are the forms, and these forms also we learned it in our previous classes, how to obtain these forms, because we essentially do 3 tests here. One is for this lamina, what we do is essentially we do a axial test where I put only sigma 1 1 in this direction, and then use the compliance relation, which will give me the Q1 S11. The compliance relation also we know, that is epsilon is essentially related to S and strain sigma. So this for each sigma how each epsilon will come out, we know, we have seen it for the 3D case. Similarly, another relation, another loading case we will consider, where we will give only in this direction, which is sigma 2 here. And by the way, this is the fiber axis. Here the fiber axis is here, so we will give the sigma 2 and 2 2 in this direction, and another is essentially the pure shear stress, where we will give this. So this gives us which is essentially sigma 1 2. So this gives us the 4 independent constants, which is E1, E2, nu 1 2 and G1 2. So essentially we found out Sij from that, and once I know the Sij, if I invert it, I get essentially the Q matrix, which is S inverse. So from there we get the Lamina constitutive equation, and how it how the engineering constant is related with the Lamina constitutive equation. So now it is important thing is here that whatever we are doing, it is in this constitutive equation, all these 1 1 2 2 and 1 2, these are the phi 1 direction and loading direction or the structural axis remains same. Now when this structural axis is essentially rotated, that means the angle between material axis and structural axis is theta here, for instance here, then how we can transfer this, that we will see. So essentially this is a Lamina constitutive equation which is this. So this is the my short form where I am in 1 2 axis, I am writing the Lamina constitutive equation. Now similarly in the xy, our objective is to find out these constitutive matrix, how it will look. So we know if we from the strain transformation relation, which we have learned also in this course in the previous class, how to transform strains. So in the strain transformation case or stress transformation case, we know what is the rotation matrix. So essentially the vector we know, if you write it, the vector or displacement we know, which is cos theta sin theta and minus sin theta cos theta, whatever is the theta. So this is a 2D case. So this is essentially rotation matrix. So this rotation matrix we can transform vectors, and from that vectors we can compute the strain and stresses similarly, then we get the transformation matrix. So this is the transformation matrix from xy to 1 2, so which is T, and T looks like this. So it is in terms of Mn, where M and N are cos theta sin theta. So now here if you want to, we know the sigma 1 2 essentially the constitutive relation in 1 2 direction we know, and in the most case when a material will be tested essentially and along the fiber direction the properties will be given. That means E1 E2 will be along 1 2 direction, and nu1 to G1 2 will be given. So when however in whatever way you want to align it or the loading axis may be different with the material axis. So in that case actually you have to find out the constitutive relation or the constitutive matrix along the structural axis. So that is the objective here, which we are deducing it here. So now this Qxx, Qxy, Qxs, Qxy and Qyy and so on, here you see that material is not essentially purely orthotropic material, and which is natural because the strength along these lines, along these fibers and these direction will be different because it will be rotated. So essentially this is the xy system where this is the constitutive axis and this constitutive relation, and this is the short form of that. Now here essentially if you find out, if you want to find out stress at xy component, you have to invert it. Now this inverse is very simple. If you substitute minus theta, it will be T inverse is T of minus theta. Essentially theta is a positive here, theta is greater than 0. So minus will be minus sin theta, cos of minus theta will be cos theta. So this will be inverse. So essentially T inverse we know. Now once I know this, our problem is to find out the next this in the xy system. Now it can be done in a little simple with a simple trick. If you now transform the strain, so if you remember that in the previous lecture I have used two different transformation matrix for T sigma and T epsilon. So, T sigma is for stress transformation matrix and T epsilon is a strain transformation matrix. But and this T sigma and T epsilon are related. So, we know that relation, but in spite of using those relations, we will not use these relations here. Instead of that, we will just check whether if I write this quantity instead of 2 epsilon 1 2, if I write epsilon 1 2, I can represent it in terms of T. So, similarly, it will be instead of shear strain, it will be engineering strain, which is epsilon or tensorial strain, whatever, epsilon x y. Now, if you do this, now this will be so sigma x y we know, which is C inverse of T inverse of this quantity. So, I now substitute the constitutive matrix for the 1 2 coordinate system, which is essentially this. Now, to remove these 2, I just multiplied with these 2. So, these 2 can be removed. So, here now this quantity again I substitute with this relation, which is essentially T epsilon x x x epsilon y y and epsilon x y. So, this quantity becomes now the transformed constitutive matrix in the direction x y. So, this is the x y constitutive relation for the material in the this fiber, this unidirectional lamina. Now, this if we multiply, so we know what is the component of T inverse. So, which is essentially T of minus theta. So, this will be minus this, the sign will be flipped essentially, and then these we can evaluate T inverse, and then T also we know. So, and Q11, Q12, Q12 and Q66, Q22 we know. So, if we write it these constitutive matrix in a proper manner, which is essentially this, which is essentially this, and so we can compute the each component of this constitutive matrix, which is sigma qxx, qxx, qxy, qxx, and then qss, qys, qy. So, it is important to know here that this is again 4 independent constant here, and this matrix looks that these terms are the 0 terms. So, these are due to the Poisson's effect, but these are the coupling coefficient where shear strain and normal strains are shear stress and normal stress are coupled here. These are the coupling coefficients. So, these coupling coefficients in 1 2 direction it is 0, but in case of a rotated direction these coupling coefficients are not 0. So, this is important here to note. So, essentially even though this material is essentially originally the in 1 2 axis it is orthotropic, but in x y axis these coupling coefficients arise. Even though these coupling coefficients are not independent, because these coupling coefficients are functions of all q1, q1 2, q1 q22 and q66 and theta, which is cos theta, which is through m and n, the cos theta and sin theta. So, essentially the 5 parameter q, these are the number of independent components here essentially are q11, q12, q22, q66 and theta. So, depending upon the theta, these coupling coefficient and actually all qxx components will be, these components will be different. So, even though material, so once again I am repeating that even though material is orthotropic originally in 1 2 axis, it is not necessary that x y axis it will be again the same structure of the constitutive matrix will be preserved. Because it is rotated, and this rotation will also depend on how the loading axis of the structure is aligned. So, this is I wanted to share with you for the lamina constitutive relation, which probably you will learn it in more detail when you will learn composite technology or composite mechanics, where how to find out a constitutive equation for a laminate will be also discussed. As laminate is essentially symmetrically or antisymmetrically placed several lamina, and through the thickness integration we can obtain the constitutive behavior of the laminate. So, this actually completes our constitutive equation part. So, to summarize, actually I summarize finally what we have learned here, what was the objective and what essentially we have learned. First of all, we started with a very general elastic material, where with the stress strain curve, and we decided to confine ourselves to a linear part of that elastic curve, which is essentially the constitutive property is essentially proportional with the means it is a constant, essentially stress is proportional to strain. So, linear constitutive equation, which is essentially comes from the which is known as the Hooke's law. So, we have derived the Hooke's law. So, first part we have derived the Hooke's law, and essentially we have derived it for the isotropic material, for which our basic knowledge from the strength of material or solid mechanics, from which we know this. So, we have derived the Hooke's law for an isotropic material, which is essentially if you remember, which is lambda plus 2 mu in this form, and if I write it in a tensorial form. So, lambda trace of E plus 2 mu epsilon. So, this is a form. So, this is trace. So, trace is epsilon kk. So, and then in a matrix form, which is lambda plus 2 mu 0 and so on. So, this we know, we have derived it for the isotropic material. We have also derived bulk modulus and first and second Lamé constant, which is essentially lambda and mu, and how it is related with the Poisson's ratios. Then we found out the relation between actually what is the physical meaning of this constant. For instance, if somebody wants to find out the material constant for a material, how do you find out? Essentially material constants are not measurable, it is a derived quantity. Essentially if you measure stress, you measure strain, and then from that you basically stress by strain you calculate Young's modulus. So, for a torsion test, for a tension test, for a shear test, we do all those tests and then found out different constants, material constants for the isotropic material. Now, once we have sufficient knowledge with the isotropic material, then we went to the anisotropic material. So, to start with an anisotropic material, we first derived the strain energy form, and then finally with that strain energy density, we introduced a fourth order tensor, which isCijkl, for a general anisotropic material where there is no symmetry is assumed, which is essentially partial derivative of the strain energy function with respect to strain. So, we have derived this thing, and with the Hooke's law in implementing the Hooke's law. So, which is again we can write this is del square sigma ij del square epsilon del sigma ij del epsilon kl. So, in this form also we can write it. So, now here with this we have introduced this fourth order tensor, and this fourth order tensor in general will have 3 to the power 4 in component, which is 81 independent material constants. So, these 81 independent material constant is essentially not all are independent. If we use that stress and strain symmetry sigma ij equals to sigma ji, and epsilon ij is epsilon ji, that is the introducing the minor symmetry. So, then we can reduce it to from 81 to we can reduce it to 36 constant. So, this is very simple essentially. If you write it 3 cross 3 cross 3 cross 3, and then this is essentially 6, this is essentially 6. So, it is 36 component, and then if you use measured symmetry, that is partial derivative, which is C I j k l, I can write it equals to C k l I j. So, which is just shifting the partial derivative. So, del square by del x del y can be written as del square del y del x. That same logic is applied, and so with that we can just arrive finally the 21 independent constant. So, with this 21 independent constant, we say this is a triclinic material. So, this is a triclinic material where there is no symmetry or reflection or even rotation symmetry is assumed. So, it is a essentially a triclinic material. Now, from there actually first we have derived the once we know the 21 independent constants, we know which coefficients are essentially responsible for it. So, we derive the Hooke's the stiffness matrix or the material constitutive matrix, which is C 11, C 12 and so on. So, we know these first 3 components are responsible for the normal stress, then these are the coming from the shear stress component, and these are the Poisson's ratio components, Poisson's ratio, and these are the coupling coefficient where the normal and the shear stress are coupled. So, from C14 to C16 these are the essentially the coupling coefficient where normal strain and shear stress are normal stress or shear stress are coupled. So, these are the coupling coefficients. Now, these are also the known as the Chentsov coefficient. So, these are the coupling between 2 shear strains essentially. So, these we know it from a general triclinic material. So, from that triclinic material we again try to reduce and define a new material, which is first we define monoclinic material where in the monoclinic material we have found out the constant is number of independent constant is 13, which is essentially done through a invariance of a strain energy function. So, since strain energy is a scalar, so it will be scalar is a invariant. So, we use that argument to derive this 13 independence constant, and for a monoclinic material actually there is a one plane of reflection symmetry. So, where det of q equals to essentially -1 if you write in terms of rotation. So, so det of q is -1 or determinant of rotation matrix is essentially -1. So, one plane of symmetry if we have, then we find out 13 independent constants, and how the constitutive tensor or this C matrix will looks like, that also we have derived. So, essentially then we define an material which is known as orthotropic orthotropic material, where instead of 13 instead of one plane of symmetry we assume another plane of symmetry or another symmetric plane. So, it since if the two planes are mutually orthogonal, then third plane is also essentially will have the symmetry. So, finally, the orthotropic material is have. 3 plane of reflection symmetry. So, that gives us the number of material constant is further reduced, which is 9, and then then this orthotropic material we again consider a plane of isotropy. If you remember the figure, this is how it is. If it is x1, then x2 and x3. So, what we assume that x2 x3 plane is essentially this plane is plane of isotropy, and then we reduce the number of material constant is 5. So, this since this is an isotropic plane, so there will be 2 material constant, because isotropic we know it for true. Then from this thing we again if we assume all 3 planes are planes of isotropy, so then we get into this, the number of constant is 2. So, then what we did is essentially these are all in terms ofCij's. So, in a void notation Cij. So, these Cij's are again related to the engineering constant. So, which we are more familiar with, like Young's modulus, Poisson's ratios, these constants. So, these constants we then again derived from 3 different tests, tension and shear test for each cases for a 3D material, and then for an orthotropic material, how these mathematical engineering constants, mathematical constants Cij and engineering constant E1, E2, nu1, 2 and so on is related. Now, then what we did is essentially how these engineering constants are bounded, that we have also derived. So, we found that for a general orthotropic material E1, E2, E3, G12, G23 and G13 should be greater than 0, and Poisson's ratios nu12, nu21, nu12, nu13 and nu23 should be less than half. So, this actually states that the Poisson's ratio cannot be arbitrarily large, and then if one of them is large, then one has to, the other one cannot be arbitrarily large, and then some restriction with the Poisson's ratios with the values of the Poisson's ratio with the relative Young's modulus. So, which is nu ij, mod of nu ij, if you remember, is less than equals to ei by ej to the power half. So, square root of ei by ej. So, those things we have derived. So, this poses some restriction on the engineering constants, which cannot be arbitrary. So, then once we done that, we then derived some material constant, derived some rotated, if the axis, structural axis and the material axis are not same, or material axis is not aligned with the structural axis, then how the constitutive matrix will look like, that also we have derived. So, the learning objective for this course is essentially even if a general anisotropic material is given, so how its constitutive relation or constitutive matrix looks like, that is our main objective. And then what are the physical meaning of these material parameter and how to obtain these material parameter, at least for an orthotropic, transverse isotropic and isotropic material, that we have learned in this module. And so, in this in the next module essentially we will start with the balance law. So, till now what we have learned is the material, first we have learned some elements of tensor algebra and tensor calculus, then we have defined what is stress strain, then so essentially we have defined strain displacement relation, and then here module 3 and module 4 we have defined how stress and strains are related. So, through a constitutive matrix, and this constitutive relation is linear for this case, and this is known as the Hooke's law. So, then once we complete third and fourth module, in the next module we will learn how a physical problem can be solved. So, basically balance laws or the conservation equations of the elastic solids. So, this completes this module. So, thank you.